Good afternoon, everyone. My name is Mansi Mundra, and I am master student at Vrije University Amsterdam. I'm here today on behalf of my group to present a paper entitled "The Impact of Instant Messaging on the Energy Consumption of Android Devices." We did this study as a part of a course, Green IT for software engineering track. One of the primary uses of mobile devices is to send and receive instant messages via messaging applications. However, no evidence is still available about how receiving instant messages impact the energy consumption of mobile devices. Today, more and more people tend to use mobile devices at a high frequency for social interaction globally. Mobile instant messaging applications continue to rise in popularity and play an important role in users' social life. According to Statistica.com, 2 billion users were accessing the WhatsApp Messenger on a monthly basis of January 2021. The problem statement for our study is that energy consumption has gradually become a major challenge for developers and mobile device vendors since it have a significant effect on user experience. The energy consumption of IM applications can be affected by the frequency and the number of instant messages sent and received by the user with their contacts. You can also see here the screenshots of WhatsApp and Telegram of user reviews where users are complaining about battery issues. With this study, we aim to access to what extent the number and the distribution of received instant messages impact the energy consumption of Android devices. In order to achieve this goal, our study aims to provide a coherent response to the two research questions. The first is the impact of receiving messages and IM application at different frequencies on the energy consumption of Android devices. Second is what is the impact of receiving messages and IM applications with different distributions on the energy consumption of Android devices. For subject selection, we use two popular messaging applications. First is WhatsApp and the second is Telegram. They have been chosen because of their high popularity and the availability of well-documented tools for programmatically sending messages to them. For the experiment, we have two independent variables, one for each research question. Independent variable for research question one is the frequency of the messages received by the application for the whole duration of the run. We defined four treatments for this variable, namely idle. The IM app does not receive any messages during the whole duration of the run. In low, IM app receive 10 messages per minute. Medium, IM app receive 25 messages per minute. High, IM app receive 50 messages per minute. We can here see the example of a trial for answering research question one. For every treatment, messages were always randomized over the 1 minute time window. For research question two, the independent variable is the distribution of arrival of the messages within a time window of 1 minute. The variable has two treatments. Even in every minute of the run, messages are received with an even distribution over time. Burst messages are received all at once at the beginning of every minute of the run. Here we can also see an example of trial for answering research question two. For research question two, we are always sending 50 messages per minute. We apply a randomized complete design for also answering research question two with the one factor of the distribution of received messages and two treatments, that is even and burst, and two subject, that is WhatsApp and Telegram. For both RQ and R1, the dependent variable is the energy consumption in joules of the Android device. We measure energy consumption by using Trippin. For the execution of the experiment, we have three main components. First one is laptop for executing the orchestration logic of the experiment and for collecting the measures from the Android device. For orchestrating the execution of all the runs of the experiment, we make the use of Android Runner. We have also given a GitHub link to the public repository of Android Runner here. Second is the Android device for running the subjects of the experiment. Um, Thirdly, the cloud hosting the API for delivering the instant messages. In the figure, we define the steps of executing the experiment. The first steps of executing a run for the experiment is to stop all the previously running apps. Second is to start the Trippin profiler. Third, in third, we firstly start the IM app to be measured, that is either WhatsApp or Telegram, depending on the plan of the runs created by the Android runner. And the second is by start collecting data about energy consumption by Trippin. For steps 4 to 8, in addition to Android runner, we use series of Python scripts to interact with each application's API and send message programmatically. We have sent message using custom Python script in interacting with applications API, which gave us the full control over the experiment execution and more flexibility on the time intervals between each message. Finally, after 5 minutes of running and profiling time, the current run is stopped and the data is collected by Trebin, is fetched and saved locally on the laptop. Um, in order to take account in order to take into account the in-centric variability of energy experiment measurement, we take the following precautions. First one is the um, order of execution of experiment run is randomized. The measurement of each IM app is repeated 30 times. Third one is between each run, the Android device remains idle for 2 minutes, so to take into account tail usage. And the fourth one is the IM apps are cleared before each run, so to reset their cache and persisted data. For the results for research question 1, we can see figure number 1, which shows visualization and summary stats of the energy consumption of the Android device across the 4 treatments of the distribution variable. We can observe that the energy consumption of the Android device grows with the increase in the number of received messages per minute. It is also interesting to note that the energy consumption of the idle treatment are very compact. This can be considered as a good indication of the reliability of our measurement infrastructure. Secondly, the variance of the energy measurement increases when considering higher frequencies of the arrival of instant messages. Figure 2 presents the measured energy consumption across 2 subjects for the experiment. It can be seen that when the system is idle or with low workload, the 2 apps consume a similar amount of energy. Differently, when the number of received messages is medium and high. WhatsApp messages tend to consume more energy than Telegram messages. Also, the energy consumption of WhatsApp tends to have a higher variance than Telegram. We have used density plots in figure number 3 to check whether the distribution of dependent variable in the 4 treatments is normal or not. The figure shows that all of the distribution in the 4 groups seems to be not normal. So for hypothesis testing, we apply statistical tests such as the Shapiro-Wilk normality test, the Lebanese test for homogeneity of variance, and the Crucial-Valley statistical test. The result of these tests provide evidence that receiving instant messages at different frequencies has an impact on the energy consumption of Android devices. For results of research question 2, Figure 4 gives an overview of the measurement data we collected across the even and burst messages distributions. The median values of the two treatments are similar. This could be the result of the same total message amount of the treatment. The mean value of even is higher than the mean value of the burst treatment due to the presence of more outliers and more data points in the first quartile. Figure 5 shows the density plots of the treatment of distribution variable. From a visual inspection, the data belonging to both the treatment seems not to be normally distributed. So for hypothesis testing, we applied the Shipper-Wilk normality test and the Wilcoxon rank sum test, which concluded that we cannot claim that different distributions of the arrival of instant messages impact differently the energy consumption of an Android device. Now we have evidence that receiving more messages leads to more energy consumption. So user can use this information, especially when their battery is extremely low. There is no significant difference between medium and high workload, indicating there must be a cutoff point at which additional messages do not add relevant overhead for the Android system. Lastly, a study did not provide evidence that the distribution of messages received on the Android device has significant impact on energy consumption. In our results, we can observe that evenly receiving messages impact energy consumption slightly more than receiving messages in the burst. We conjecture that the slight difference might be due to the tail energy consumption, that is the phenomenon where components such as the network card remain in high power states after completing a task. On one hand, end users can trust Android platform when dealing with sudden bursts of messages, which might not drain the battery of their devices. On the other hand, developers could use this information to develop new features for their IM applications, such as advanced do not disturb mode. Future work consists of a replication of the study targeting a higher number of subject apps and performing per app statistical analysis. We have also provided a GitHub link to the public repository here if anyone is interested in replication. And second, to conduct an experiment targeting additional open source apps and inspecting how they internally manage the reception of instant messages. Third, to investigate how push-up notifications are managed at the OS level in Android, how the use of mechanisms can be linked to the results we obtain in this study, and how such a knowledge might help improving the energy consumption of Android devices. So for the summary of the study, first, we aim to investigate two research questions. First was, what is the impact of receiving messages and IM apps at different frequencies on energy consumption of Android devices? Second was, what is the impact of receiving messages and IM applications with different distributions on the energy consumption of Android devices? Um, for subject selections, we'll use WhatsApp and Telegram as our two instant messaging applications. And finally, results of our study provides evidence that receiving instant messages can reduce the battery life of a user's Android device, even when the number of received messages is really relatively low. And lastly, there is no significant difference when receiving instant messages um, by WhatsApp or Telegram, either evenly per minute or in burst. Thank you for watching.